All right, quarter 3 study guide, here we go. Busy, gotta go. Okay, G and N are two matrices. So we've got G times N equals Gn, obviously. If Gn is a 3 by 5 matrix, N is a 4 by 5 matrix, then what does G have to be? So let's call this, I don't know, H by K. So in order for the matrix multiplication to be defined, these two dimensions have to be the same. So we know the second dimension of G has to be 4. So that's already an error. And then the outer dimension has to be this 3 to match that. So if we have a 3 by 4, we call H equals 3. 3 by 4 times a 4 by 5, it becomes a 3 by 5. So the answer should be 3 by 4. So that should be 3 by 4. Let's call this B. Okay, moving on. The directrix of the parabola is, okay, so what do? We've got our standard conic form. Let's first find the vertex. Vertex is going to be -2, comma, +2 based on this. Then this is our 4p value. 4p is 10. Therefore, our focal length is a +2.5. So if we sketch this right quick, we get -2, comma 2. Since y is squared and p is positive, we're going to be looking something like this. So our directrix should be behind at a distance of 2.5. So if that's -2, comma 2, we need our directrix, wow, it's loud, to be an x value and needs to be 2.5 to the left of -2. B. Matrices. In the matrix, K is a constant. If A does not have an inverse, what is the value of K? So we want K to be singular, no inverse, which means the determinant of A has to equal 0. A square matrix will have an inverse as long as the determinant is non-zero. Okay, so what is the determinant? The determinant is A times D minus C times D. We want that to be 0, so we want -K plus 2 to be 0. We want K to be 2. We could double check that, right? 2, -2, 1, -1. Another way to check this is if one row of the column of the matrix is a multiple of the other. Here, row 2 is 1/2 times row 1. That would have no inverse. Okay, the matrix below is an augmented matrix representing the system of equations in x, y, and z. If C is a constant, for what value of C will the system have infinitely many solutions? So for infinitely many solutions, we're looking for the bottom row to be all zeros, right? So it looks like we're gonna have to do some elementary row operations to try to see what the last row can become. So let's first do use the second row to eliminate this -3. Try to get it closer to reduced row echelon form. So if we do 3 row 2 plus row 3, keep row 1 the same. Times this plus this is 0. 3 times -2 is -6 plus 6 is 0. 3 times -3 3 times -1 is -3 plus C. negative 3 plus c. In other words, think about what this means. This gives us an equation, 0x plus 0y plus 0z equals negative 3 plus c. This equation is not true if this is anything other than 0. But if this is equal to 0, then we would have 0 equals 0, which is always true. So what do I mean? I mean this simplifies to 0. 0 equals negative 3 plus c. In other words, c equals negative 3 would make, if this were 0, negative 3 plus c is 0, then if we get 0 equals 0, it should be infinitely many solutions. In other words, if c equals 3, there's infinitely many solutions. And if we really wanted to, we could, how about we just do that? We see what happens. So if we replace c with 3, and see, verify what we get here. And there we go, we get, well, same concept. We get a bottom row of zeros. This is already reduced row echelon form. And it's implying that there's infinitely many solutions. Which of the following is one of the foci of the ellipse with the equation below? Okay, so let's just go part by part with an ellipse. We've got a center of 0, 0. This is going to be a ellipse with a vertical focal axis. In other words, the major vertices are going to be here, the foci are going to be here, kind of a thing, and it's going to be like this. But let's get more information. So we've got here, the way I define it is always I take the bigger one to be a squared. The denominators are always a squared and b squared. I always define the bigger one as a squared, the smaller one as b squared. It doesn't really matter. And then for, oh, you have to, no, sorry, take it back. The bigger one doesn't have to be a squared. Because for an ellipse, this is the Pythagorean identity we use. A squared has to be the biggest. It's equal to the sum of the other two squares. So we get 60 equals 20 plus c squared. We need c to find the foci because c is the focal length. So solve this for c. C equals square root of 40. Square root of 40 can be written as square root of 4 times 10, which is 2 square root of 10. And since this has a vertical focal axis and the center is at 0, 0, this c value of 2 square root of 10 means that each focus is 2 square root of 10 away from 0, 0. So for instance, this would be 0, 2 square root of 10. The answer is C. Okay, free response question about parabolas. The directrix and the focus of a parabola are shown in the graph below. Graph the parabola showing at least 3 specific points on the parabola. Okay, if all we have is the focus and the parabola, how could we do this? Well, remember the definition of a parabola is it's a set of points that is equidistant between a point called the focus and a line called the directrix. So first thing, the vertex is always going to be directly between the focus and the directrix. So just see here that we have an x-coordinate of 2 and an x-coordinate of 6. The x-coordinate of the vertex has to be directly between. We need the vertex to be 4, 3. And that's one of our 3 specific points. Now, the next 2 points you can always get from a parabola is to think there has to be, so we're going to be opening to the left because we need to have that focus inside and we need to have the directrix kind of outside of the parabola. So we know we're going to have 2 points on this line. In other words, 2 points with an x-coordinate of 2. So, and every point on this line is going to be the same distance from the directrix. Every point on this line is going to be a perpendicular distance of 1, 2, 3, 4 away from the directrix. So if every point on this line is 4 away from the directrix, we just need these specific points that are 4 away from the focus. Starting at the focus, going 1, 2, 3, 4 up. This point here is 4 away from the focus and 4 away from the directrix. Do the same thing down here. 1, 2, 3, 4. This point is 4 below the focus and 4 away from the directrix. So what we have here is 3 points on the parabola, and we can kind of just, the rest, kind of get an idea that this is going to be flattening out like that, something like that. So that's good enough. So the only things we need to define the equation of the parabola are the vertex and the focal length. So if we have the vertex, we know it's going to be, and it's because it's got a horizontal focal axis, horizontal axis of symmetry. We know it's going to be y squared and x here. Y minus 3, x minus 4. And then the focal length is the distance from the vertex to the focus is 2. Therefore, 4p, which always goes here, is 8. There you go, and you can verify. A good habit is to verify. Let's see, is the point 2 comma negative 1 in fact on satisfying this? Well, negative 1 minus 3 squared, is it equal to 8 times, question mark, negative 2? No, it's not. I made a mistake. Good thing I checked. The distance here is 2, but remember focal length is a directed distance. So since it's a focus is 2 to the left of the vertex, it should be negative 2. So that should be a negative 8. Okay, the point P on the parabola, point P is on the parabola and has coordinates negative 2k. K is a negative constant. What's the distance from P to the focus? So P is some point down here. We don't know. We're not going to need to know. What we do know is back to the definition of a parabola. If this point has an x-coordinate of negative 2, we know its perpendicular distance to the directrix. The distance from P to the directrix, x equals 6, is absolute value of negative 2 minus 6, it's 8. If you're going from this point to the directrix, the quickest way is to go 8 units to the right. So the distance from P to the directrix is 8, and by definition, the distance from P to the focus must be equal to the distance of P to the directrix, also 8. All right, here we go with the exercises. So solving systems of equations, my first idea is always elimination. So I'll look here. If I do a quick check, I can eliminate x if I multiply the first equation by negative 2. I like to always multiply by something that allows me to add to avoid subtraction. So if I add these, I get y, negative 5y plus 6y is y equals negative 14. Substitute back into any equation. I'll substitute back into the original equation 1. And then just solve that. So we get 2x equals negative 30. So x is negative 15, and we get negative 15 comma negative 14. Okay, 2b. Okay. We could solve for y and we could use substitution, but look, we got two parabolas here. We just add them together, 1 plus 2, we get 2x squared equals 6 plus x. Ooh, I don't know if this is going to be the easiest way. Maybe we could have subtracted and eliminated the x squareds, but I'm just charging ahead because we can always solve a quadratic. So I'll move everything over, set it to 0, solve by factoring, for instance, 2x times x. What a truth. Multiply the leading coefficient and the constant, get negative 12. We could get negative 12 by doing negative 4 times 3. So this could also be written as 2x squared minus 4x plus 3x minus 6 equals 0, which can be factored to 2x plus 3, x minus 2 equals 0. So we get x equals negative 3 halves, or x equals 2. And you can solve that by substituting back in. Substitute back into the first equation. Negative 3 halves squared plus y equals 6. Y equals 6 minus 9 fourths. So one solution is going to be negative 3 over 2 comma. That's 24 over 4 minus 9 over 4. That's 15 over 4, I believe. And then here we've got, what if x is 2? Still using equation 1. Y equals 2, that's nice. So intersection of two parabolas, there we've got two solutions. Like I said, I like to do elimination. Sure, why not? Let's do 2 times the first equation is 12x plus 6y equals 18. Let's do negative 3 times the second equation is negative 12x minus 6y, negative 18. Okay, look, something interesting here. It appears that one equation is just a multiple of the other. That means it's similar to when we had the matrix where one row is a multiple of the other. That case is always going to mean, sorry, I'm thinking of the inverse. The question about no inverse because one row is a multiple of the other. That's telling us something is happening. I'll get to the point that what's happening here is there's infinitely many solutions because 0 equals 0 is always true if we add those together. So since these are lines, that means these are the same line. So our solution is, there are infinitely many solutions. If you want to express your solution, you should solve one of the equations for one of the variables. For instance, if I solve this for y, that means that x can be anything. It's a line. The system has a set of solutions that is infinitely many points on the same line, where x can be anything, but whatever x is, y must be negative 2x plus 3. That is the solution to that system. Okay. Matrix inverses. Find the determinants and the inverses of the matrices below. So the determinant, remember we can use this bars to represent the determinant. It's going to be 1 times 2 minus, here be careful, AD minus BC, be careful with negative, so I'm writing this out. So the inverse is negative 2. So the determinant, the determinant is negative 2, so the inverse is going to be 1 over the determinant times the adjugate. The adjugate, remember, is this rearrangement where we switch A and D, and then for the other diagonal, we change the sign. So the inverse should be negative 1, negative 1, negative 1, negative 1/2 is the inverse. Okay. 6 minus 0. Be careful. For whatever reason, people always make mistakes here. I find a lot of people make mistakes when there's a 0 here. 2 times 3 is 6. 6 times 0 is 0. So the determinant is just 6. So the inverse is 1 over 6 times the adjugate, which again we swap the main diagonal entries and we make the other entries opposite of what they would have been before. 1/2, negative 1, 0, 1/3. Let's see. What does it say for us here? Find the matrices below. No, sorry. Find the determinants and the inverses. If no inverse exists, call the matrix singular. Okay, I can predict what's going to happen, right? So the determinant of this guy. Well, look, I can already tell the determinant's going to be 0 because the bottom row is negative 3 times the first row. If one row is a multiple of the other, you're going to have no inverse. What does that mean? That means you're going to get a times t is negative 9 minus negative 1 times negative 9 equals 9 minus 9, which is 0. That means this is singular, no inverse exists. Which, by the way, means if you made a system of equations with these coefficients, you'd either have no solutions or infinitely many solutions. For the matrices below, calculate the product and or state that it does not exist. Okay, so BC is going to be 1, negative 1, negative 3, 1, 2, 0 times 3, 0, 0, 1. A 3 by 2 times a 2 by 2 will exist, and it will be a 3 by 2. Let's go part by part. We're going to dot this row with this column, which is going to be 3 times 1 minus negative 1 times 0. Then we're going to stay with the same row, but dot it with the next column. It's going to be 0. I should be careful. Sometimes I mix up it's not going to matter, but right, matrix multiplication, we're adding the products. So here we're going to have 0 plus negative 1. 0, negative 1. Well, I'm in the canteen in case you couldn't tell, and the workers are, letting out a lot of stress, chatting about who knows what at the end of a long day. I gotta talk louder than them. 0 plus 1. So here we go, negative 8, 1. And then lastly, 2 times 3 plus 0 is 6. And 0 plus 0. 6, 0. Probably talking about the boss, right? Oh, this boss keeps getting on my back. Maybe he's talking about you guys, the students. Okay, AB. 1, negative 2, 0. Negative 2, 2, 1. Do you think are they speaking Mandarin or are they speaking a dialect? I can't tell. Okay, so here we got a 2 by 3 by a 3 by 2. It should actually be 2 by 2. So 1 times 1 is 1. Negative 3 times negative 2 is 6. 0 times 2 is 0. Okay, then we're going to have first row dotted with second column. Negative 1 minus 2 plus 0. So we're going to get 7, negative 3. Oops, sorry about that. Negative 2, 1, negative 2, minus 6 plus 2. Negative 6. 2, 2, 0, 4. Okay, and guess what? I'm gonna just cram it in here. AC should also exist, I believe it's a 2 by 3. Oh, AC should not exist, wow. So A is 2 by 3, C is 2 by 2. Inner dimensions do not match, AC does not exist. Alright, yeah buddy. Alright, more matrices, number 4. Matrix D has order 3 by 6. What will be the order of product AD using the matrix A from the previous question? Oh, you gotta switch up the order on me, eh? A is 2 by 3. So if we do AD, therefore AD is going to be a 2 by 3 by a 3 by 6. It will exist because the inner dimensions match. And the result will be a 2 by 6 matrix. AD is 2 by 6. 5. Solve the following matrix equations given A, B, C below. Alright. Okay, so, well, let's do it like this first. AX plus B equals C, a matrix equation. We are trying to solve for X. Is that clear from the statements, or should I specify? I'll probably edit that to make that clearer. So what do we have here? We'll just treat it like a real number equation. We have AX equals C minus B. And then whatever that result is, in order to isolate X, we need to multiply in the front by A inverse to quote-unquote cancel out A. And we would need to multiply in the front by A inverse over here. So let's do this. What's C minus B? C minus B is negative 2, 2, negative 5, 4, minus 1, 6, 0, 1. So C minus B is negative 2 minus 1 is negative 3, 2 minus 6 is negative 4, negative 5 minus 0 is negative 5, 4 minus 1 is 3. And then we need to multiply that by A inverse. What is A inverse? Well, we actually found it in an earlier problem, but I'll re-show the work here. So we got X is going to be A inverse times 3, negative 4, negative 5, 3. Let's find A inverse. A inverse is going to be, well, the determinant of A is 2 minus 4. The adjugate of A is 2, 1, 2, 2. So the inverse is 1 over negative 2 times 2, 2, 2, 1. So A inverse is negative 1, negative 1, negative 1, negative 1 half. So I will put that. Remember, because matrix multiplication is not commutative, we multiply by A inverse in the front here. We have to multiply A inverse in the front here to keep it equal. So then we're just doing our matrix multiplication. Negative 3 plus positive 5. 4 minus 3, 4 plus negative 3. Negative 3 plus 5 over 2. 4 minus 3 over 2. So our result should be 2, 1. Negative 1 over 2. 5 over 2. That looks right to me. Trust me. And then I think we're just going to fit in B here, and then we'll call it a paper. How do we solve for Y here in A equals B, Y, C? Well, we need to get rid of the C, we need to get rid of the B. We can get rid of the B by multiplying by B inverse in the front. So that will give us the equivalent statement that B inverse A equals YC. And then we need to multiply by C inverse in the back. So we need to multiply in the back here, and we'll get y equals B inverse A times C inverse. That means I need to find B inverse, I need to find C inverse, and I need to multiply them in this particular order. Oy, gewalt. What is B inverse? Okay, come on. Keep positive, you can do this. 1 over the determinant is 1 minus 0. 1 minus 0, 6 times 0 is 0. Times the adjective of B is 1, 1, negative 6, 0. So B inverse is 1, negative 6, 0, 1. That's good, not too bad. C inverse is 1 over the determinant of C is negative 8 minus negative 10. It's going to be 1/2, I believe. Adjugate, negative 2, 5. So C inverse is, I like to show my steps. I like to be careful, so let's just show the steps. 1/2, 4, negative 2, 5, negative 2. So I'm going to write it out now. So y is going to be, B inverse is 1, negative 6, 0, 1 times A, 1, negative 2, negative 2, 2 times C inverse is 2, negative 1, 5 over 2, negative 1. Almost there, come on, we can do this. Row by column is going to be 1 plus 12 is 13. Negative 2 minus 12, negative 14. 0 minus 2 is negative 2. 0 plus 2 is 2. All right, y is then 26. I'm just gonna write it out to be careful. 26 minus 35, negative 13 plus 14, negative 4 plus 5, 2 minus 2 is 0. Oh boy. No chance I made a mistake here. Looks beautiful. Okay, use augmented matrices in row echelon form to solve the following systems of linear equations. Okay, so what's the logic here? Remember, for our augmented matrix, we're going to take all the coefficients and put them as entries of a matrix. So we've got 1x plus 2y minus 1z equals 3. Constants go on over here. 3, 8, negative 5, 11. Negative 2, negative 3, 7, negative 5. Watch, this is going to take me 2.5 minutes max. Let's go. You know why? Because I am going to be strategic. I'm going to say, I'm going to use this 1 to get rid of the other stuff. Negative 3 times row 1 plus row 2. That will get rid of that leading 3. I'm also going to do 2 operations at once. So negative 3 plus 3 is 0. Negative 6 plus 8 is 2. Positive 3 plus negative 2 is positive 3 plus negative 5 is negative 2. Negative 9 plus 11 is 2. Okay, 2 row 1 plus row 3, we'll get rid of the negative 2. 4 plus negative 3 is 1. Negative 2 plus 7 is 5. 6 plus negative 5 is 1. Okay, looking good. Now, I got 2 things I could do. One, I could swap these to have the 1 there. Or, you know what, watch this. What am I doing here? I'm going to do something kind of crazy. I am going to, watch this. See if you can keep up. I'm going to do negative row 2 plus row 1. Watch what will happen. Negative 0 plus 1 is 1. Negative 2 plus 2 is 0. Positive 2 plus negative 1 is 1. Negative 2 plus 3 is 1. Now I'm going to do negative 2 row 3. Because why did I do that? Because I wanted to get that 0. I didn't actually have to do that because I don't even think I'm going to go to reduced row echelon form. I'm just going to go row echelon form, but hey, it won't hurt. Negative 2 times row 3 is negative 0 plus 0 is 0. Negative 2 plus 2 is 0. Negative 10 plus negative 2 is negative 12. Negative 2 plus 2 is 0. Interesting. And I'll just leave this. So really, this is neither row echelon nor reduced row echelon, but I have... well, fine, I'll just go one more step. Technically, I've already really got all I need. But let me just do this. I'll keep the first row. I will switch row 2 and row 3. Bargain. And then I'll multiply this previous row 2 by negative 1/12. I mean, we can pretty much see what it's going to be, but I'll do it anyways. Negative 1/12 divided by times negative 12 times negative 1/12 is 1. 0 times negative 1/12 is 0. So what does this imply? This implies this is row echelon form. This is one of the possible row echelon forms. And it's implying here that z equals 0. 0x plus 0y plus 1z equals 0. Okay, well, that means this second row implies that y plus 5z equals 1. We can now back substitute and say, okay, therefore y plus 0 equals 1, so y equals negative 1. Or sorry, y equals 1, not bad. And then if we substitute it into here, we've got x. The first row is x plus 0y plus z equals 1. And z equals 0, so x plus 0 equals 1. Therefore, x equals 1. So we've got our solution. And if we would have gone to reduced row echelon form, we would have got 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 0. No, sorry, 0, 0, 1, 0. But this is our solution. Okay, let's try another one. That took me more than 2.5 minutes, my bad. Okay, 2, negative 5, 7, negative 3, 1, negative 2, negative 3, 5, negative 1, 3, negative 10, 8. Oh, and by the way, right, there's more than one way to get this to row echelon form. This is just the way I chose. So like here, there's going to be more than one way also. For instance, right now, I'm going to use this one to get rid of the other stuff, and eventually I'm going to plan to move that to my first row. So watch what I do. Negative 2 row 2 plus row 1. All I want to do is to get a single 1 in the first column and everything else 0. So I don't have to start with the element 1, 1. I can start with element 2, 1, which I'm doing here. Negative 2 plus 2 is 0. Positive 4 plus negative 5 is negative 1. Positive 6 plus 7 is 13. Negative 10 plus negative 3 is negative 13. Keep the second row. Row 2 plus row 3, 0, 1, negative 13, 13. So if I just do some rearrangement here, you know what? Forget the rearrangement. Watch what I'm about to do. Now I will rearrange. I'll do a row 1, switch to row 2. All right, I'll just do it. And row 2 with row 3, whatever. I'm gonna just put this down at the bottom basically. So I'll just move everything up. Don't worry about the notation so much. And what do I notice here? I notice that this row is a multiple of that row. So again, I'm going to get that situation where we have infinitely many solutions. I'll just finish it off to do that. If I do row 2 plus row 3, oops, sorry. You know what? I will try to get it a little bit further along to reduced row echelon form. So this implies I'm going to keep the middle row the same, row 2 the same. If I add row 2 to row 3, I get all zeros. That's what implies the infinitely many solutions. And if I do 2 row 2 plus row 1, I can get 1, 2 times 1 is 2 plus negative 2 is 0, negative 26 plus negative 3 is negative 29, positive 26 plus 5 is 31. This is actually reduced row echelon form because every row that has a leading 1, excuse me, every column that has a leading 1 has zeros elsewhere. And if there's no leading 1 in the third or fourth column, we can have other things there. This implies there are infinitely many solutions. A bottom row of all zeros implies that. And we could express the solutions by saying the second row means that 1y minus 13z equals 13. So if we allow z to be anything, z can be a free variable, and we solve this for y, then what we have is z can be anything, leave it as a variable, but whatever it is, y must be 13z plus 13, and then x, what must x be? Well, we need to have an equation for x, so let's do that. Let's do 1x minus 29z equals 31, x equals 29z plus 31, 29z plus 31. So when there's infinitely many solutions, the concept is let one variable remain undetermined and then express the other variables in terms of that variable, such as this. All right, reduced row echelon form. So let me try to say the rules for reduced row echelon form verbally. The rules are you need to have the first non-zero entry of every row is a 1, which we call a leading 1. So in the second row here, the first non-zero entry is this 1. In the third row, the first non-zero entry is another 1. So this matrix matches that first rule. Let's go through the first rule with all of them. Does the second matrix meet the requirements of the first rule? First non-zero entry is 1, good. First non-zero entry is 1 again, good. And if there's no non-zero entry, it's still not breaking that rule, so this also passes the first rule at least. But how about this guy? The first non-zero entry of the first row is 1. First non-zero entry of the second row is 1. But because the first non-zero entry of the third row is not a 1, C is not yet reduced row echelon form, I'm going to have to change it. And I can do that very simply by doing 1/2 row 3. That's easy enough. Now we have 3 matrices that pass the first rule. What are the other rules? The other rules are that every leading 1, which is that first non-zero entry, has to be to the right of the leading 1 above it. So this leading 1 is to the right of this, leading 1 is to the right of that, pass second rule, pass second rule, and this leading 1 also to the right. So basically that means that, another way you could say it is if you think about the element notation, like this element is A33 for instance. Every leading 1, the row number has to be less than or equal to the column number. Like you can't have a leading 1 in A21. And then lastly, to be reduced row echelon form, every leading 1 has to be the only non-zero entry in its row. Oh, sorry, scratch that. The only non-zero entry in its column. So here, one of these is gonna fail. This leading 1 is the only non-zero entry in its column. Good. This leading 1 is the only non-zero entry in its column. But this leading 1 is not the only non-zero entry because of this. So A is also not reduced row echelon form yet because it fails that last rule. This, however, this leading one is the only non-zero entry, this leading one is the only non-zero entry, and there's no other leading one. So B is the only one that was in reduced row echelon form. B needed no steps to get to reduced row echelon form. C, we already did a step, but is this in reduced row echelon form? Also no. This leading one is the only non-zero entry. This leading one is the only non-zero entry. This is not a leading one, doesn't matter. This is a leading one though. We need to get these to become 0. That will be quite simple, but we need to do that step to get it to reduced row echelon form. So all we need to do, we keep the bottom row the same. It's very simple. If you have a 0, 0, 1, or if the only thing in a row is 1, then you could just use it to clear that stuff out. So, okay, let's just do it. -3 row 3 plus row 2. It's going to be 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 0 is 0, but -3 plus 3 is 0. And then -4 row 3 plus row 1. That is reduced row echelon form. And by the way, if this were an augmented matrix, this would imply the system has no solutions because it would be 0x plus 0y plus 0z equals 1. It would be 0 equals 1. No solutions. But it is reduced row echelon form. And then lastly, to get this to reduced row echelon form, we just need to get rid of that. So if we would to simply do -1 R3 plus R1, 1, 0, 0. -2 plus 0 is -2. 0, 1, 0, 1, 0, 0, 1, 2. That's now reduced row echelon form. And by the way, we have kind of all three types of augmented matrix here. We've got this one is one solution, z equals 2, y equals 1, x equals -2, one solution. This no solutions, this infinitely many solutions. Okay, let's keep going. If each of the matrices below, oh, yeah, 8 is asking about what I just said. It should say that. So if each of the matrices above is an augmented matrix for a system of 3 equations, x squared z, write the solution. So A, we got it to this reduced row echelon form, which implies x equals -2, y equals 1, z equals 2. So I like to put it in an ordered triple, just like you have an x-y pair, you could have x-y-z triple, -2, 1, +2. B is this one right here. This implies 0x plus 0y plus 0z equals 0. That's infinitely many solutions, so we want to express it in terms of a free variable. So if we allow z to be free and we use the second row to say y equals 1, we do have a solution for 1, interesting. But the first equation implies x plus 0y plus z equals 2, means that if we let z be anything, we can solve this equation for x in terms of z by subtracting z from both sides. So we could write an ordered triple here where x has to be -z plus 2, y is always going to be 1, and then z is left free, z is anything. So when you have infinitely many solutions, you can still express the solution, but the solution will include a variable. And then C is no solution because the last row here is saying 0x plus 0y plus 0z equals 1 is never true. No solution. So what we have in C is like, well, this doesn't make any sense straight away. This doesn't make sense straight away. But you already knew it's going to be no solution. We did have to get some work to get it to reduced row echelon form, but we didn't need to do that in order to get the solution of no solution. Okay, The table below shows the ticket sales of 3 different types of tickets at a theater over 3 nights and the amount earned in sales each night. What is the price per ticket of each type of price? What is the price per ticket if each type? What is the price per ticket of each type if the prices are constant each night? Okay, this is just a system of equations. 80 orchestra tickets at a certain amount, 80 times X, plus 120 mezzanine. That's a different number, let's call it Y, plus 200 times Z equals that. So we could solve it using a system of equations. Let's see how long it takes me to solve it using a augmented matrix. Okay. So it looks like we can do some cleaning up if we just divide everything to reduce it down. Let's multiply the first row by 1 over 40, which is equivalent to just dividing each thing by 40. 2, 3, 5, what's 10,800 divided by 40? Like 25, no, 250. And this will be something, okay, well, it's not gonna be that bad. It's 242 divided by 1.8. How many times does 1.8 go into 28? Please tell me I didn't make a mistake. 1. Oh man, it's not looking good. I think I made a mistake. All right, for these problems, we could just plug in, but I'm gonna graph it. So, we've got here 2x plus 10y equals 30 means that 0, 3 is an intercept and 15, 0. So this is not going to be to scale, but let's just hope it works anyways. So we got this, and 0, 0 means we're going to shade underneath it, because we're going to shade, the fact that you plug in 0, 0, you get zeros less than or equal to 30, you plug into that. And then we're going to get a downward parabola. So by the way, it's 2, 4, a solution. Well, okay, let's just plug in. So 2 times 2 plus 10 times 4, is that less than or equal to 30? 4 plus 40 is not less than or equal to 30. So 2, 4 is not a solution already because it's not a solution of the first. And then this parabola is going to have a vertex of 1, 2. It's going to have a focal length of -4. No. It's going to have a focal length of -1. So it's going to be 1, 2, down 1. It's going to be something like this, which is going to include 0, 0, because if you plug in 0, 0, okay, if you plug in 0, 0, you get 0 minus 1 squared. Is that less than or equal to -4 times 0 minus 2? Well, 1, is that less than or equal to 8? Yes. So 0, 0 is a solution to both, but 0, 0 only. Okay, this one I'm going to draw it more accurately. So, six x plus 4y equals 24 is going to have intercepts at 0, 6 and 4, 0. All right, so I can get away with a sketch that has not that many grid lines. 1, 2, 3, 4, 5, 6. 0, 6. 1, 2, 3, 4. And so it's gonna look like this. 0, 0 is a solution because 0 plus 0 is less than or equal to 24. So we're gonna shade everything including 0, 0. And then x squared minus 4. This is vertex form. We can just go 1, 2, 3, 4 down. And then we can just graph the parabola old style, no focus. Over 1, up 1. Over 2, up 1, 2, 3, 4. It will intersect at 2, 0. And negative 2, 0. And we're shading above the parabola because its y is greater than. Y is greater than or equal to x squared minus 4. Shade above parabola. So 0, 0 is in this region. 0, 0 is a solution, check. And 2, 4. 1, 2, 3, 4. 2, 4 is not 2, 4. 2, 4 does not satisfy the linear equation. 6 times 2 plus 4 times 4. Is it less than or equal to 24? 12 plus 16 is not less than or equal to 24. 2, 4, not a solution. Okay, draw one more sketch. X squared plus y squared is less than or equal to 4 is a circle with radius 2, center 0, 0. So we get this guy, circle. And then a line, y is greater than or equal to 2x plus 3. That slope intercept form should go 1, 2, 3. Up 2 over 1, it's something like this. Okay. So is 0, 0 a solution to this? Yes. So we shade inside the circle. And then is 0, 0 a solution to y is greater than or equal to 2x plus 3? Was 0 greater than or equal to 0 plus 3? No. So don't shade that, we shade this part only. The solution is just going to be that. So neither. All right, linear maximization problem. We're going to use the 4 constraints to get a feasible region. If we got this ax plus by form, I like to use the intercepts. So 0, 6 would be the y-intercept. 8, 0 would be the x-intercept. And likewise for this, 0, 10, and 5, 0. So I need the y to go up to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we'll do this one first. The x-intercept of this is 1, 2, 3, 4, 5. So we've got something like this. And then for the first constraint, we've got 0, 6, 1, 2, 3, 4, 5, 6, and 8, 0. So this was 5, 0, 6, 7, 8. Okay. If we're doing less than or equal to both of them, then that means 0, 0 is the solution for both of them. So our feasible region is going to be here. Because x greater than or equal to 0, x equals 0 is the y-axis, x greater than or equal to 0 is to the right, y is greater than or equal to 0 is above the x-axis. So we know our corner points. I'm going to put it right here. Corner points. We've got a quadrilateral. We're going to have 4 corner points. We need to find the value of the objective function at each corner point, 10x plus 5y. We've got 0, 0. We've got this guy was 0, 6. We've got this was 5, 0. And then the last corner point is going to be the intersection of these two lines. It looks to be about 3, 4, but let me verify by doing. Treat our constraints as equations to find the point where the two lines intersect. So if we do -1 times this, -3x minus 4y equals -24, and add it, we get 5x plus 0 equals 16. Oh, good thing I solved for this. X equals 16 divided by 5 is 3.2. 3.2 comma something. Let's plug it back into the first equation. 3 times 3.2 plus 4y equals 24. 9.6 plus 4y equals 24. Therefore, 24 minus 9.6 equals 4y. So that's 24 minus 10 would be 14. So this would be 14.4 equals 4. Y divided by 4 divided by 4. Y equals 3.6. Going fast and loose. I'm pretty sure that's correct. Yeah, sure, because it would be 7.2 divided by 2. Yeah. Okay, so now we got to evaluate at each corner point. 0 plus 0 is 0. 0 plus 30 is 30. 50 plus 0 is 50. And then here we go. 3.2 times 10 is 32. Plus 3.6 times 5 is 18. No, you're kidding me. Another 50? Really? Serious? Okay, fine. So the maximum value is, sorry, the minimum value is 0, the maximum value is 50. So this would imply that that any point on this segment is giving you the maximum value. And why we got that is because the objective function has the same slope as this particular constraint. Right? They both have a slope of 2, I believe. -2. Okay, but either way, minimum value is 0. Maximum value is 50. It's just a little bit weird that the maximum value here occurs at not just these two corner points, but any point along this boundary. Okay, find the vertex, focus, directrix, and focal width of each of the following parabolas. Okay, all right, keep chugging along here, chug-a-lug. Okay, so we've got a vertex of -4, 2. We've got y squared, so it's going to be a horizontal parabola. 4p equals 12, therefore p equals 3. So we have here, I'll just sketch it, I like to sketch it. -4 to, just a sketch, not going to be totally accurate. Opening to the right, p equals 3 implies that we're going to go 3, to the right, so that's going to be -1, 2. So the focus is -1, 2. And the directrix is on the other side, 3 to the left. X equals -7. And focal width is 12. B. Draw this one a little bit more accurately, eh? So if we got this, it's not quite the old standard conic form that you want, because you want the constant together with the linear factor. So we multiply both sides by 10, that's all it's going to take, and now we've got this more usual form where we've got a vertex of -4, 2, and we've got a 4p of 10, so the focal length is 2.5, and we can sketch this accurately as having a vertex at 1, 2, 3, 4, 1, 2, -4, 2. Because x is squared and it's a positive focal length, we're going to go up. And particularly, we're going to go up 2.5 to get to the focus. So up 1, 2. That point is going to be at a coordinate of -4, 4.5. Because we're going on a vertical axis based on the x squared. The directrix is 2.5 in the other direction down here. So the directrix will be y equals -0.5. So let's write this out. Vertex, -4.2, -4, 2. Focus, -4, 4.5. Directrix, y equals -0.5. And focal width will be 10. And why not just see what that looks like? That means we're going to go 1, 2, 3, 4, 5 to the right. 1, 2, 3, 4, 5 to the left. And this is the focal width. The length of the latus rectum. Okay, I'm going to finish one of these off and I'm going to take a break. Oh, I just did C. My bad, that's C. Where's B? Oh boy, I need a break. So B, let's just do a simple adjustment to make this y minus 0 squared equals, factor out the constant x plus 3. That will make it a little bit clearer that the vertex is -3, 0. That'll make it also a little clear that the focal width is 4, or say that the focal length is 1. I'm just going to do this off the dome. Because this is horizontal and the focal length is positive, we're going to the right to find the focus. So what's 1 unit to the right of -3, 0 and -2, 0 is the focus. The directrix is going to be to the left. That's going to be x equals -4. And the focal width, as I stated, is 4. All right, here we go, number 13, ellipses. Okay, so for ellipses, we can use the same logic as we find the vertex of a parabola to find the center of the ellipse. So the center here is going to be +2, 0. That's going to be the center. Then we need to use these values underneath. The denominators are going to be the a squared, then the b squared values. The bigger denominator is always the a squared, the smaller denominator is the b squared. And then we use the Pythagorean relation a squared, since it's the biggest one, is equal to b squared plus c squared. Remember, usually we see the Pythagorean theorem, we always think a squared plus b squared equals c squared. That's only if c is the hypotenuse of the right triangle. So don't get confused by that a squared plus b squared equals c squared. Because we define a squared as the biggest length in the ellipse, it's a squared by itself is equal to the sum of the other two. So a squared equals 25 plus c squared. Therefore, c squared equals 25 in this particular ellipse, so c is 5. So what that means is if c is 5, a is square root of 50, so a is 5 square root of 2. So a is the distance to the vertices. So if we start at 2, 0 in the center, we're going to go 5 square root of 2 to each vertex. So 5 square root of 2 is approximately, what is that? 5 times 1.4 is, let's call it 7. So it's to 9, 1, 2, 3, 4, 5, 3, 4, 5, 6, 7, 8, 9. It's approximately here. That's going to be 2 plus 5 square root of 2, 0. So it's really 2 plus or minus 5 square root of 2, 0. Because our a value is 5 square root of 2, we will, that's the distance on either side to the vertices. And by the way, so 1, 2, 3, 4, 5. Let me get to my point. By the way, we're calling the vertices the major vertices. Some other places call them the major vertices, like the endpoints of the major axis. And since, oh, I messed this up. Darn! This is all wrong. Well, not all wrong. But the reason that these are wrong is because the fact that the bigger number is underneath y, a squared is underneath y, that tells you this is going to have a vertical focal axis, which means instead of going approximately 7 to the right, 7 to the left for the vertices, we're going to go 7 up, 7 down. 1, 2, 3, 4, 5, 6, 7 up, not here, not here, and 7 down. So that means all this work was wrong. That means that we're staying at an x-coordinate of 2. We're not moving left or right to go to the vertices. We're going up or down. So we're going up 5 square root of 2. We're going down 5 square root of 2. Those are the vertices. And it will actually be a little bit easier to find the foci because the foci are dependent on the c value. That's the distance from the center to the foci. So this foci are just 1, 2, 3, 4, 5 up. 1, 2, 3, 4, 5 down. And it's the b value is 5, so they're going to go 5 to the right. It's going to be, oh boy. Okay, that was not so great. I mean, I'll try to do better on this next one, but that's the correct answer. Okay, let's try this again. So what was the mistake in the last time? A squared and b squared are our denominators. A squared is the bigger denominator. Okay, we correctly last time found c squared. Let's do that again. So c squared equals 9, c equals 3. Now, pause. After we find the center, which is negative 2, 5, 1, 2, 3, 4, 5. Now pause and say, the fact that the bigger denominator, which we always call a squared, is under the x value means that we're going to have a horizontal focal axis. That means it's going to be a wide parabola instead of a tall parabola. So now, if our center is at negative 2, 5, and now we have a horizontal axis, it's the y value that will stay the same for all of these. The y value for all 4 of these points will be 5. And we're going 3 to the right and left to find the foci. So 1, 2, 3. So here's a foci at 1, 5. And here's a foci at 1, 2, 3, negative 5, 5. These 2 points can be thought of as the center, which is negative 2, plus or minus the focus, or excuse me, the c value. 5. And the vertices, on the other hand, are dependent on A. A squared is 25, so A is 5. And so the vertices are going to be 3, 5, and -7, 5, because the vertices can be thought of as the center plus or minus A. So should I try to draw this? I don't know if I can. I don't really have much space. Didn't ask me to draw it. Why am I drawing it? Well, it's too late now. B means that from the center we're going to go up 4, 1, 2, 3, 4. We can call these the minor vertices, 1, 2, 3, 4. And it looks something like this. Oof, that's not very good. And these are our foci. But this is our answer right here. Okay. 14. Foci and asymptotes of each of the following hyperbolas. Okay, similar concept, but let's contrast this when we get there with the work we just did for the ellipse. So here I'll just do an adjustment and make that y minus 0 squared equals 1. So I'm going to sketch this, I guess. Why not? Center, same logic as the ellipse. Center is at -3, 0. Now, to find the vertices, we need A. To find the foci, we need B. Now here's the difference. No difference. A squared and B squared are still going to be our two denominators. We can still call A squared the bigger one and B squared the smaller one. It's not going to matter. Is it? Oh, it is going to matter. Sorry, guys. Here, in the ellipse, we always choose A squared as the bigger one. In the hyperbola, I like to say A squared is the one under the positive term. So here, if we call A squared 16, because 16 is under the positive, Y has a negative in front of it, X has a positive. That tells us that our focal axis will be horizontal. We're going to have a hyperbola that opens left and right. And that tells us that this A value is how we get to our vertices. 1, 2, 3, 4 to the right, and 1, 2, 3, 4 to the left. So our vertices will be 1, 0, and -7, 0, which is basically our center of -3 plus or minus the y value, 0. Okay, and our foci, now here's a difference with the ellipse. For our foci, the c squared is the biggest. Now pause, how do I remember that? Well, I remember that c in both of them is how you get the foci. In an ellipse, the foci are closer to the center than the vertices. However, in a hyperbola, the foci are further from the center. In other words, C is bigger than both A and B. And so C has to be the combination of A and B to get the size that it needs. So when we find this, we're adding A squared plus B squared. C squared is 25, C is 5, and that checks out because the foci should be 5 to the right. So there's a focus, and the other one is over here. So we've got 2, 0, and we've got -8, 0, which in other words is our center, plus or minus the C value. And then I won't draw that asymptotes because we're not asked for the asymptotes. Wait, we are asked for the asymptotes. La. Okay, I'm getting a little bit tired today already, you can see. Okay, well that's not too bad. There's a trick to find the asymptotes. To find the asymptotes, more than one way we can do it. Well, I'll just do this way. If we have the b value, we can make a nice little box. What do I mean? I mean, starting at the center, go 4 over, because a is 4, but then go 3 up. If we do that, in each direction, 4 over 3 up, and then 4 over 3 down. And we use this rectangle to make a x through the diagonals of the rectangle. That x is giving us our asymptotes. These two lines are the equations of our asymptotes. So what's the equation of those lines? Well, we can use point slope form. We've got a point going through -3, 0. So we've got y minus 0 equals something x minus -3. And then what's the slope? Well, it's rise over run, up 3 over 5. Up 3, excuse me, over 4. 1, 2, 3, 4. Up 3 over 4. There it is. And the other one, it's going through the same point. The only difference is it's down 3 over 4. Down 3 over 4. I'll show you the other method to find the asymptotes over here. Okay. So here, I'll try to clear up what I said before. Here, okay, let's start with the center again, though. Center of 1, -4. So I'll make my plane look like this so I got more space for 1, 1, 2, 3, 4. Now, the a squared and the b squared are the two denominators. In an ellipse, the a squared is the bigger one. In a hyperbola, let's make the a squared the one under the positive. Now, it turns out coincidentally that the one under the positive is the biggest one. Just like over here, the one under the positive was the biggest one, but that doesn't have to be the case. If we always define a squared as the one under the biggest one, or excuse me, a squared as the one under the positive one, that's going to give us our vertices. Because we always want to say the positive one determines our focal axis. What I mean here the y squared term is positive. That means we're going to have a vertical focal axis, which means from the center we're going to go up square root of 34. A is square root of 34. Up square root of 34 to find the vertices. Square root of 34 cannot be simplified, but it's approximately 6. So 1, 2, 3, 4, 5, 6, something like this for the vertex. 1, 2, 3, 4, 5, something like this. So that's going to be a vertex, that's going to be a vertex. But we're asked to find the foci. So the foci, again, are going to be further away. So we need c squared as the sum of those two. So c squared equals 34 plus 30 is 64. C equals 8. So the foci are 8 away from the center, which means the foci, pardon myself, sorry, are going to be, the center was 1, -4. They're going to be 8 away from that up and down. So 8 up is going to be 1, +4. 8 down from that is going to be 1, -12. Now the asymptotes. Now we could do the box. Those are the asymptotes over here. We could do the box again, and you could say, okay, we're going to go square root of 30 to the right and make a box and go like that. But here's the other trick you can use. If you replace the 1 with a 0, that will give you the equation of the asymptotes. What do I mean? So we've got the same equation, but replace this with a 0, then what we will have is we can move the term with the x over. And if we solve this for y, it it will give us our asymptotes. So if we multiply by 34 on both sides, we get y plus 4 squared equals 34 over 30 times x minus 1 squared. Doesn't look like a line yet, but if we take the square root of both sides, we get y plus 4 equals plus or minus square root of 34 over 30, and the square root of x minus 1 is x minus 1. Sorry, square root of x minus 1 squared is x minus 1. So we get the asymptotes. Y equals whatever this is, square root of 34 over 30. It's not an integer, but it is a constant. Times x minus 1 minus 4. That is a line. And that will be one of the asymptotes. And the other asymptote will be negative 34 over 30, x minus 1 minus 4. And those are the two asymptotes. So you could have done that over here too. You could have said, okay, set this equal to 0. You get x plus 3 squared over 16 equals y minus 0 squared over 9. Multiply both sides by 9. You get 9 over 16 times x plus 3 squared equals y squared. Square root both sides, you get 3 over 4 x plus 3 plus or minus that, and then there you go. That's your answer. Oof. Okay, hopefully this one will be quicker. Eccentricity of each of the conic sections from 13 and 14. Well, eccentricity is just the c value over the a value. So let's get after it. In number 13, a, we had c equals 5, a equals 5 square root of 2. Therefore, e is 5 over 5 square root of 2, which is 1 over square root of 2, which is square root of 2 over 2, which is, by the way, less than 1. Which makes sense because we need an ellipse to have it, eccentricity less than 1. 13, we get c equals 3, a equals 5. So the eccentricity is 3 over 5, which is 0.6. So ellipse has eccentricity less than 1, between 0 and 1. If it's a circle, it's 0. And then 14a, got a hyperbola, which should be greater than 1. 14a, we got c is 5, a is 4. So the eccentricity is 5 over 4, or we could write that as 1.25. In fact, greater than 1. And then 14b, we got c is 8, and a is approximately, so a is square root of 34. So c over a, the eccentricity is 8 over square root of 34. Should I try to, oh yeah, let's just rationalize the denominator. It won't really matter, but we get, remember this was approximately 6, right? So we get like 8 times 6 is 48 over 34. It's greater than 1 anyways. 4 rad 34 over 17. Okay, so eccentricity is something that all conic sections have. Ellipses, it's between 0 and 1. Hyperbola is greater than 1. Which would help us answer this question right here. Which conic section has the following eccentricities? 0 is the eccentricity of any circle, because a circle has a c value of 0, right? E equals 0 over a. A is like the radius. And since circles, the focus is basically the same as the center, 0. B, 0.5 is less than 1, therefore it has to be an ellipse. C, 1.4 is greater than 1, therefore hyperbola. Anything greater than 1 is a hyperbola. By the way, our textbook does not talk about the eccentricity of a parabola, but every parabola has an eccentricity of 1. Greater than 1 hyperbola, greater than 1 hyperbola. C value is always bigger than the A value for hyperbola. Foci are always further away from the center than the vertices in a hyperbola. For each of the following equations, if the equation is a parabola, state its vertex. If the equation is a hyperbola or ellipse, find its eccentricity. Okay, we're almost to the end here. So for these ones, I like to put the x's first, y's second, but only put the x's first if we have an x squared. We don't. If only one of the variables is squared, move the other variable to the other side. So I'm going to move the negative 12x over here. I think this will work out. I'm doubting myself, but I shouldn't. Okay, we can complete the square here. We need a term to add on here. Y minus 4 plus 16. I added 16 to the left-hand side. I got to add 16 to the right-hand side. So y minus 4 squared, you get negative 12x plus 96. Y minus 4 squared equals, factor out the negative 12x minus 8. Here we go, it's a parabola with a vertex of 8, 4. Not bad. Okay, here we have an x squared and a y squared, so I'm going to put the x's together, leave a blank. I'm going to put the y's together, leave a blank. Move the negative 72 over. I need to complete the square for both x and y. X minus 8 squared will give us what we need there, which means we need to add 64, which means we need to add 64 to the right-hand side. For y, I need to add 3. That means I need to add 9. So what we have here is negative 72 plus 64 is negative 8, plus 9 is 1. Oh. What do you know? What is that? Well, it's got both x and y squared, so it's not a parabola. It's either a hyperbola or an ellipse, because they're both positive. It's adding. That's an ellipse. But wait, a squared and b squared are both 1. What does that mean? That means that a squared, well, in an ellipse, a squared equals b squared plus c squared. So that means that c squared is 0. That means that the distance from the center to the focus is 0. This is a circular ellipse. It's a circle. So what is the eccentricity of a circle? 0 over 1 is 0. Technically an ellipse, but it's a circular ellipse. Or just a circle. Okay. Last one. Again, we've got both x squared and y squared, so we're going to pair the x's, leave a blank. Pair the y's, negative 9y squared plus 18y. I'll move the constant over. We're going to have to do it eventually anyways. Now, this is going to be a little bit trickier because of that negative 9, but shouldn't be too bad. Okay, complete the square for x. I had to add 4. Add 4. Now, here, I need to factor this out. I didn't complete the square yet, but I factored something out. I'm just gonna take it a step at a time. I need to still complete the square here. So watch what I'm about to do. Okay, now I can complete the square. This becomes -1 squared. Now, I'm adding 1. -1 squared is 1. But really, I'm not just adding 1. I'm adding 1 inside parentheses with that factor outside. So really what I'm adding is -9 times 1. Anytime you have factored that out when you're completing the square, you got to account for that when you're balancing the equation. So this becomes -27 minus 9 is -36. Now, conic form that we like has equal to 1. If it's something x squared plus y squared equals 1, both positive, ellipse. This is going to be a hyperbola because it's going to have that negative there, but we need to get that, we don't want that there. So what are we going to do? If we divide everything by -9, no, that won't help us. Sorry guys, my bad. What we want to do is get that equal to 1 there. If we divide by -9, it's just going to become +4. It doesn't solve our problem. We want to divide by -36. So if we divide everything by -36, what do we get? Well, actually, now we get the negative over here. We get -x plus 2 squared over 36. That's nothing happening over there. -9 over -36. -9 over -36 is the same thing as +1 over +4. So we get this equals 1. That's a hyperbola. And it's going to be a vertical axis, vertical focal axis, because the y is the thing that's positive. Okay, finally here we get an example where we can define A as the thing under the positive. Not necessarily the bigger, the thing under the positive. A squared is 4. B squared is 36. So C squared equals 36 plus 4 is 40. C equals square root of 40. So the question asks us for the eccentricity. So we get A equals 2, B equals 6, C equals square root of 40, which is 2 square root of 10. And so the eccentricity is 2 square root of 10 over 2 is square root of 10. Okay, this exercise is based on the definitions of the geometric definitions, or also called the locus definitions of each of the conic sections. So we just have to stop back and think about it. Okay, so what's true about a parabola? Parabola, every point on the parabola is equidistant to the focus and directrix. So, if P to F1 is 20, then that's saying that the point to the focus is 20, then the point to the directrix also has to be 20. The distance from any point to the directrix is the same as the point to the focus. We could also say Q to the directrix is 25. For an ellipse, different. For an ellipse with a second focus F2 where the distance P to F2 is 10, what's true about an ellipse is all the points, ellipse, the sum of the distances to each focus is constant. So what does that mean? It means P to F2 plus P to F1 must equal Q to F2 plus Q to F1. So if we got two foci, F1, F2, pick a point, P to F1 plus P to F2, whatever that sum is, and then we take another point, Q, those two distances have to be equal to that. So P to F2, it's telling us is 10, P to F1 was 20, Q to F1 is 25, and then so we're trying to find Q to F2, it must be 5 to equal 30. So Q to F2 is 5. Any point you pick on here and you add the distances to the two foci, it will be 30. And then lastly, hyperbola is like a ellipse, but the difference of the distances is constant. So hyperbola. Okay, so let's see. P to F2 is 30. P to F1 was 20. Do I dare draw a sketch of this? I'm gonna try. So here's a focus. Here's a focus. So P to F2 is bigger. So P must be like over here. So this is 30. This is 20, obviously not to scale. The difference between them, difference is 10. So Q to F1 is 25. What must Q to F2 be? Well, we need something that has a difference of 10. So is there actually two possibilities here? Could it be 15 or 35? I think it could be 15 or 35. Depends on if Q is closer to F1, then that's 25 and that's 35. But if Q was over here, then it would be 15. 19. Sup? Okay, I'm out of my red pen. Can't find a pencil, so they don't make any mistakes. All right, so 19a, equation of an ellipse. Ellipse, we're gonna have x, y, both squared, both positive, in other words, addition equals 1. Start with the center. The center is -1, 2. So it's going to be +1, -2. Then we need the denominators based on this distance here, this distance here. A shorter distance we call b, so we're going to call b equals 2. And the longer distance we call a equals 4. So that tells us b squared is 4, a squared is 16. And we put the larger number underneath the axis. So it's a vertical axis, vertical focal axis. Put the larger number underneath y. Now, do not leave until you've checked your answer. What do I mean? Well, look, 1, 2 has to be on this ellipse. 1, 2. Plug in 1, 2. Do you get a true equation? 1 plus 1 squared over 4 plus 0 over 16. Is it equal to 1? Yes. There you go. Boom. Bingo, bango. B. Same concept. We've got a center. Center is 3, 0. x minus 3 squared. Y minus 0 squared equals 1. What's the difference? We're going to have a negative sign somewhere, but I'm not putting it yet. Well, sure, I can put it now. Because this has a horizontal focal axis opening left and right, it's the y that should be negative. Check this at the end, but if it were x negative, it would be opening up and down. Okay, similarly, a is, well, no, not similarly. A is going to be, well, this is similar to the up, sorry. A is the distance from the center to the vertex. But now how do we find B? We need the asymptotes, which we have. So remember, one way to get the asymptotes, you use the A to go over, use the B to go up to make this rectangle. And then the asymptotes will go through the diagonals. So here the corner is 2 units up. That implies that B is 2. Now, ellipse, the larger number goes underneath the variable that determines our axis, vertical axis. Put the larger number under y. Here, we always put A underneath the positive one. In other words, we always put the distance from the center to the vertex under the positive one. So first we got to get A squared. Nine, 4, check. We have the point 6 comma 0 should be on our hyperbola. Let's plug it in and check. 6 minus 3 squared over 9 minus 0 squared over 4, is it equal to 1? 3 squared over 9 minus 0 equals 1, yes. And then last but not least, the parabola. We've got a vertex of negative 2, 2. We've got a horizontal focal axis. Horizontal focal axis means that y is going to be squared. Vertex is negative 2, 2. X minus negative 2, y minus 2. Focal length is, well, the vertex is at negative 2, x equals negative 2, the focus at x equals 1, that's a focal length of 3. Hence, 4p equals 12. Throw a 12 in there. Check. Pick a point. It appears that 1 comma 8 is on our parabola. Let's check 1 comma 8. If we plug in 8 for y, plug in 1 for x, 6 squared, does it equal 12 times 3? 36 is equal to 36. Checkerino. Okay. Graph each of the following equations. Okay, we're so close. 20 a y minus 2 squared equals negative 2x minus 2. Vertex, find the vertex first, it's 2 comma 2. 4p is negative 2. I like to say, okay, I got the vertex. I know it's going to be opening to the left now, so I can start my picture. Give myself a little more positive values because my vertex is at 2, 2. The focal length is negative 1/2. So our focus is going to be right here. This is going to be a tight squeeze. Our directrix is going to be here. Well, this is not easy to graph because, okay, remember we can get our vertex right here. then we can get to 2 points along the lattice rectum. So we want a point that is on the same x value as the focus, which is 1.5. 1.5 is 1 away from the directrix, so we want to go 1 away from the focus. So this point at 1.5 comma 3 and 1.5 comma 1 should be on the parabola. I don't know if my y-intercepts are accurate, but the focus, I believe, is accurate of 1.5 comma 2. Go. No time to waste. Okay, we've got a ellipse here because we've got both x and y squared, and we've got addition, both positive. So we're going to have a center of 3 comma 0. Since the greater denominator is under x, it's going to be a wide ellipse, horizontal focal axis. So let's just take the whole space for this. One, 2, 3 comma 0 is our center. Our greater denominators are a squared value. Our smaller denominators are b squared value. Our a squared is equal to our b squared plus our c squared. So 49 equals 4 plus c squared. So c squared equals 45. So c equals square root of 45, which is going to be 3 rad 5. I have to clean these tables or I'm done. Okay, let's go. We're almost there. So our major vertices are a away from the center. A is 7. So our vertices are going to be 3 minus 7 is negative 4 comma 0. 3 plus 7 is 10 comma 0. 4, 5, 6, 7, 8, 9, 10. Our b value is 2. That tells us we're only going to go up 2 to get what we call our minor vertices. And so we get this weird looking ellipse that is so narrow, so wide, you could say. That's not bad. That's better than I usually get. And the foci will be 3 square root of 5 away from the center, which is, what is that, like 4.5? 1, 2, 3, 4.5, somewhere like this, I think. 1, 2, 3, 4.5, something like that. Let's call that F1 and F2. Whatever, 3 minus 3 square root of 5 comma 0, and 3 plus 3 square root of 5 comma 0 is C. Now we've got a hyperbola because both x and y are squared, but we've got one of them as a negative now. So we've got a center of 0 comma 2. We've got our positive, y is the positive. We're going to have a vertical focal axis, and therefore our foci are going to be up and down from the center. Because that's the positive one, let's put this over here. That's our a value. Our b value is instead 4. And remember, the foci are the furthest away in a hyperbola, so c squared is so big it needs a squared and b squared to combine to get it. C squared is 20. C is square root of 20, which is 2 square root of 5. So our vertices are going to be 4 up, from this. 1, 2, 3, 4. And 4 down. 1, 2, 3, 4. And then our foci are going to be 2 square root of 5. That might be more than 3. Wait, what? It's got to be more than 3. If A is 4, then C has to be bigger than 4. Oh, square root of 5 is going to be... Oh, man. What? Oh, square root of 5 is bigger than 2. Come on, man. Square root of 5 is bigger than 2, so this is going to be bigger than 4. Let's just say there's something like this. I don't know. Foci are going to be somewhere beyond the vertices. Now, to accurately graph the parabola, we need to find the asymptotes. So let me do the AB method. From the center, I went up 4 to get to the vertex. If I go over 2, that's the B value, on each side of the vertices, I can make this rectangle that can guide my asymptotes. The asymptotes are going to go through the corners of that rectangle. This is the vertex, and since they're asymptotes, the hyperbola is going to basically be getting closer and closer to those dashed lines. Something like that. And real quick, I'll show it one more time. How can you get, another way you can get the equation? If you do this, x squared over 4 plus y minus 2 squared over 16, set it equal to 0, solve for y. Multiply both sides by 16. Square root both sides. Plus minus square root of 4x squared. So y equals 2 plus or minus 2x. So y equals 2x plus 2. Y equals negative 2x plus 2. Yes, both of these asymptotes have a y-intercept of 2. One goes up 2 over 1. One goes down 2 over 1. Good. All right, almost done. Let's finish it up so these people can eat their dinner. Okay, last one. The hyperbola so-and-so has that as an asymptote. What is K? Oh, I can do the same trick I just did. To find the asymptote, I can do, instead of equal to 1 as that hyperbola equation has, replace the 1 with a 0, solve that for y. Don't get ink all over this, I already told you. Multiply both sides by k. Oh lordy, is this gonna work? K over 9x plus 1 squared. Therefore, y equals plus or minus square root of k over square root of 9 is 3 times square root of x plus 1 squared is x plus 1. So that's not good. So square root of k equals 3 over 2. Let's change this to 2/3. Square root of k equals 2. Square root of k equals 2. Therefore, k equals 4. Excuse me. That was bad. Vertex negative 1, 2. Well, let's just do the most logical thing. Factor out the x. Oh, that's interesting. K over 4. That matches the y value of the vertex. How do we get this to match the x value. K over 4 has to equal negative 1. Therefore, k equals negative 4. Yeah. Good enough. And last but not least, no solution. Therefore, we want these to be two lines that have the same slope. There's more than one way to do this. You want it to have the same slope, but different intercept. So, well, let's just do this. The slope of this, isn't the slope of this negative a over b? Negative 3 over negative 8, which is 3/8. The slope of this is negative a over b. We want that to equal 3/8. Therefore, negative k equals 12 over 8. Therefore, k equals negative 3/2. Boomba. Oops, sorry. There you go.